Yeah, you want to torque it though?
Oh, you got it tight.
The goal of the El Nino Rapid Response Experiment is to look at how changes in the weather patterns, the evaporation of moisture in the tropics, how that has changed during a major El Nino event like the current one out there, and then to look at how those changes further impact the weather on the west coast of the United States. My name is Gary Wick. I'm a physicist with the NOAA Earth System Research Laboratory Physical Sciences Division in Boulder, and I'm on assignment to the Unmanned Aircraft Systems program within NOAA.
Boy, that was the easiest we ever did it.
During this campaign, we have 4 instruments on board the Global Hawk aircraft. The first is a dropson system, which it deploys these very small sensors, much like weather balloons that go up, but these go down. So these small sensors, they're about the size of a paper towel roll, and as they fall, they collect very high resolution, vertical resolution measurements of temperature, humidity, and wind speed. So they give us a very detailed picture of the atmosphere.
Yeah.
In addition to that, we have the Hamster, which is a microwave sounding instrument, and that provides sampling much like one of the weather satellites that is used extensively in our weather models. The third instrument is HIRAP. It's a Doppler precipitation radar. So just like the weather radars on the ground, we're flying a radar on the aircraft which gives 3-dimensional coverage of precipitation, of rain droplets, and with information from those rain droplets, we can derive continuous measurements of the wind speed in the atmosphere. The final instrument is the NOAA ozone sensor, which provides measurements of ozone concentration at the flight level of the Global Hawk. The Global Hawk provides amazing capability for this experiment just in its ability to be airborne for up to 24 hours or more. That by being aloft for that long, we can sample a large range of the ocean, almost like a satellite does. That with the Global Hawk, we get very detailed sampling like an aircraft, but with the endurance that a satellite would give us. So we're able to sample this large area and look at changes in the atmosphere that wouldn't be possible with other traditional manned aircraft.
My name is John Newhouse. I'm a Deputy Project Manager for the NASA Global Hawk program. I'm actually a commissioned officer with the NOAA Commission Corps. I've been flying the Global Hawk here at NASA for 4 years as an aircraft commander and instructor pilot. So as you can see here, the Global Hawk has no yoke or stick to fly with. We use a mouse from takeoff to landing, climb and descents when we're underway. Everything is automated in the Global Hawk. So all I need to do is do a mouse click here on the screen to say takeoff or to land, climb, descent, maintain an altitude. Everything is done by this mouse click. And it's very much like flying an autopilot in a manned airplane. And what NOAA is using this is as a study to use unmanned aerial vehicles over high-impact weather events such as hurricanes, and in this campaign we're actually using it over El Nino events in the Pacific. We're going to be working with Air Force C-130s, we're going to be working with NOAA Gulfstreams, and also a NOAA ship, the Ronald H. Brown. So we've got C-130s covering one part, G4 covering another part, the ship covering other stuff, and then we're going to be in the parts that are harder to reach.
We typically take off at first light so we can get to the area of interest to study El Nino weather per the science requests. This usually takes about maybe 8 hours to transit to the area that we're studying. And once we're there, we spend several hours analyzing all kinds of weather phenomena that has piqued the interest of the scientists. And it usually takes about 8 hours to bring the plane back home. So that gives us about a total flight time of 24 hours for each sortie. I'm Herm Posada, and I'm a UAS research pilot here at NASA Armstrong Flight Research Center, and I fly the Global Hawk for airborne science. While we're flying the aircraft, we're monitoring many screens. Mostly we're looking that we're on the right track that science has requested us to fly on. We are also obviously looking at various parameters of the aircraft, make sure we don't get any trouble with airspeed, altitude, or the heading. The flight plans continuously gain updated as science changes the area of interest. Obviously these storms are moving and we are trying to keep up with them.
Hey, mission pilot.
So in the Global Hawk Operations Center during a flight, we're going to be monitoring the flight with this wonderful mission tool suite capability that NASA has developed. And with that, it allows us to see the data coming in from the aircraft in real time, satellite data, and multiple things for us to really see what's happening as we go along. And so what we'll be watching for is, can we see the weather patterns? Can we see patterns in the humidity that let us know that we're sampling the areas that are eventually going to move downstream and impact the U.S.? The Global Hawk is a one-of-a-kind capability that, NOAA, we have a great observing system from satellites to aircraft to ships, but there's nothing that provides the capability of the Global Hawk. So within NOAA, we really want to see if that is a really good addition to our current observing system. And so by collaborating with NASA, we get this wonderful opportunity to test its capabilities, see its impact on the forecasts, and then hopefully that opens the door for a broader collaboration down the line to do this on a regular basis.
Copy, and release will be in any right turn away from you.